Hey, if anyone can hear me, can you type something in live chat? I want to see how it works. Uh, or Discord if you can't type anything in live chat. Okay, awesome. So live chat is usable. So wonderful. And so how's the audio? Can you guys hear me fine? Okay, good. So, today we are going to finish up with some stuff that we started last time. So, before we begin the new stuff, I want to talk about what we did last time because it was a little complicated. So, we introduced this notion of elementary matrices. The reason we introduced the notion of elementary matrices is because we were really interested in these row operations. And we have been using these row operations to solve linear systems. Now, the cool thing about elementary matrices is that they let you conceptualize each of these three row operations in terms of matrix multiplication. So for example, if you want to interchange the ith row with the jth column, which is an elementary row operation, for a given matrix A, all you have to do is take a matrix of this form and multiply. This row operation corresponds to matrices of this form. Likewise, you can look at an elementary row operation where you multiply a row by a non-zero real number. And this is an elementary matrix that accomplishes it. And finally, you can replace a given row by its sum with a multiple of another row. And this corresponds to an elementary matrix that looks like this, where what this is doing is it's saying that row J is going to be equal to row J plus M times row I. So the three row operations correspond to multiplication by elementary matrices. And this gives us a way of computing the inverse matrix. So let me remind you how that works really quickly. Say we have a matrix A, like maybe we'll go do something that's pretty easy to start with. 1, 5, how about 6 here, and 1 here. So say we have a matrix like A, and we want to compute its inverse. Well, what we can do is we can form the augmented matrix. The augmented matrix is the matrix where you have A, and then you have a bar, and then on the other side, you have the identity matrix, in this case, the 2 by 2 identity matrix. So we would have 1, 5, 1, 6, and then 1, 0, 1, like that. And what we try to do is we try to do a sequence of elementary row operations. And what we want to accomplish is we want to make the matrix on the left here into the 2 by 2 identity matrix. But by doing that, what you accomplish is you turn the matrix on the right into the inverse of A. So let me just do this example out. What I could do looking at this augmented matrix is I could first take row 1 here and subtract it from row 2. So row 2 is going to be equal to row 2 minus row 1. And this corresponds to multiplying this matrix and this matrix by a matrix of this form. And if I do that, then I'm precisely going to get 1, 5, 1, 0 for the top row, and then 0, 1, negative 1, 1 for the bottom row. And now this matrix right here is almost in reduced row echelon form. In fact, it is in row echelon form. But to put it in reduced row echelon form, what we have to do is we have to clear this 5. So what I have to do is I have to subtract the bottom row from the top row. So if I do that, then I get row 1 is equal to row 1 minus, I have to multiply this by 5, 5 times row 2. And by doing that, I have succeeded in making the matrix on the left into the identity matrix. And let's see what happens on the right. Well, I'm going to have negative 1, 1 on the bottom because I'm not changing the bottom row. Here I'll have a negative 5 because I'm subtracting 5 times 1. And then here I'm subtracting 5 times negative 1, which means I'm adding 5, so I'll have a 6 here. So this matrix right here is going to precisely be A inverse, and we can verify that real quick. So we have 1, 1, 5, 6, and we can multiply it through by 6, negative 5, negative 1, 1, and we'll see what happens. Well, actually let me do this the way I usually do it, so align things nicely. Take this, pull it down here, and go through the process of computing the matrix multiplication. If I multiply this column with this row, I see right away that I get 1. This column with this row, I see I get 0. This column with this row, I get 0. And this column with this row, I get 1. So this thing right here is definitely the inverse matrix of A. So this is how we use elementary row operations to compute matrix inverses. And now I want to introduce another notion. So we shall say an n by n matrix is, hold on, let me check in my notes what it's defined as. How does the book call it? We shall say an n by n matrix A is row equivalent to a matrix B if there is a sequence of elementary matrices E1, E2, all the way up to EK, such that B is equal to EK times EK minus 1 times blah, 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 E1 times A. So the idea is that A is row equivalent to B if after performing a sequence of row operations to A, you can obtain the matrix B. And I should also just say here that the matrix B should be n by n as well. So this is the notion of row equivalence between two different matrices. And with that in mind, I can now state the main theorem of the chapter. There are three equivalent conditions for a matrix to be non-singular, where non-singular here means the matrix is invertible. One is that, the definition of non-singularity. The second is that if you look at the linear system AX equals 0, it has only the trivial solution, 0. And finally, C, A is row equivalent to I. So here's how this is proved. Let's take our matrix A and let's suppose A is non-singular. Thus it has an inverse. So what we can do is we can look at the equation AX equals 0, and we can multiply both sides through by A inverse. And if we do that, we get A inverse times A times X is equal to A inverse times the 0 vector. And this ends up being the same thing as the identity times X. And this is the n by n identity. Equals, if you multiply the 0 vector by anything, you just get 0. And if you multiply X by the identity, you just get X. So this implies that X is equal to 0. So X is uniquely determined. And is equal to 0. So this completes the proof that A implies B. Now I'm going to look at the proof that B implies C. So we'll go down here. And the way I'm going to do this is I am going to look at the augmented matrix A underscore X. So this is actually A underscore 0. Hold on for 1 second. Maybe I want to denote this slightly differently. So suppose AX equals 0 has a non-trivial solution. Maybe we'll call it Y. then okay, never mind. This isn't easier. I'm going to go with the original approach. So we're going to look at the augmented matrix A bar 0, and we can perform Gauss-Jordan elimination. And if you recall, this is exactly what we do when we're trying to solve a linear system. And the way you do Gauss-Jordan elimination is you just perform a sequence of row operations. And so eventually, after running the algorithm, you get some matrix here, E, and you'll still have a 0 on the other side of the pipe. And E is going to satisfy some criteria that we talked about before. So let me remind you of what those criteria are. So, going back a little bit. First off, the matrix needs to be in, well, not first off, it's essentially everything. The matrix needs to be in reduced row echelon form. So, after applying Gauss-Jordan elimination, you get something like this. So the matrix E is in row echelon form, and the first non-zero entry in each row is the only non-zero entry in each column. So the matrix E has to look something like this. Maybe you have a 1 here, and then 0, 0, 0, 0 here. Or, actually, maybe I'll give a better example. Maybe you have a 1 here, a C here, a D here, and then down here you have 0, 0, 0, 1, and then blah, 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 so on. Above this 1, you have to have 0, and below this 1, you also have to have a 0. And so this is what it means for something to be in reduced row echelon form. Now, the thing is, if there's ever a gap between the 1 in a given row and the 1 in the next row that's longer than 1 column, you'll notice something that happens. Namely, that there is there's a vector y such that a times y is equal to 0. So, for example, in this one, I could take the vector c, -1, and then zeros elsewhere. And this would be a vector that if I multiplied it by this matrix, I get 0. So, if E is not IN, then there is a non-trivial solution to AX equals Y. So if we're assuming B, which is that AX equals 0 has only the trivial solution 0, and we run Gauss-Jordan elimination, the only option that you can get is that the ones that are appearing, the kind of leading pivotal ones, have to appear in consecutive columns. So I'd have to have a 1 here, a 1 here, a 1 here, all the way down the diagonal. Otherwise, you can craft solutions to this system that are non-trivial. This shows that B implies C. So now we've shown that A implies B, and we've shown that B implies C. The final step of the proof is probably the easiest, and I've essentially already proved it, which is that we have to show that C implies A. Now, if A is rho equivalent to I, this means that there exist matrices E1, E2, all the way through to EK, such that I is equal to EK times EK minus 1 times blah, 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 E1 times A. Now, here's the key fact that we use. Let me put that over here slightly. Each EI is invertible. So for example, I can multiply by the inverse of EK, the inverse of EK minus 1, and so on. And if I do that, then I find that A is equal to E1 inverse times E2 inverse times blah, 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 EK inverse. On the other hand, I could also just take the product of these things, and I could call the product B. And this would exactly mean that I is equal to B times A, and this is precisely what it means for something to be non-singular by the definition that we adopted. So we're able to conclude that all three of these conditions are equivalent. Now, I want to talk about one last thing concerning row operations. And it's kind of a special case, but it's something that comes up in a lot of computational applications. So let me go back and recall our elementary row operations. Suppose a matrix A can be reduced to upper triangular form using only operation 3. Then by applying the same sequence of operations to I, where I is the identity matrix, we obtain a matrix L that is lower triangular. And L times U is equal to A, where we're calling the upper triangular form of A U. So this is one of those results that is best shown in practice. And it'll make the most sense if we do it that way. So I'm going to do a 3x3 example. Suppose I'm looking at the matrix 1, 5, 7, 3, 2, 4, -1, 10, and 1. I'm going to try to reduce this to upper triangular form using only operation 3. And as I do it, I'm going to actually apply the operations to an augmented matrix. So my augmented matrix here is going to be 1, 5, 7, and then I'll have a bar 1, 0, 0, 3, 2, 4, 0, 1, 0, and -1, 10, and 1, 0, 0, 1. Now, watch what happens when I subtract 3 times row 1 from row 2. So row 2 is going to be equal to row 2 minus 3 times row 1. So say we apply this operation. Let's see what happens. Well, the first row stays the same, so I have 1, 5, 7, 1, 0, 0. And then I subtract 3 times row 1 from row 2, so I'll have a 0 here. And then I'm subtracting 15 from 2, so I'll have a -13 here. A 3 times 7 from 4, so that would be -17. And then over here I'll have -3, 1, 0, and then the bottom row stays the same. So note that by applying a single row 3 operation, I haven't changed anything above this diagonal. The only thing I changed was the 0, and the 0 became a -3. Because in fact, whenever you're applying these row 3 operations, going through the standard kind of Gauss-Jordan algorithm, you're subtracting a higher row from a bottom row. So we can keep going through the process. Say now I add row 1 to the bottom row. And by doing that, I'll cancel out this -1. So row 3 is equal to row 3 plus row 1. First 2 rows stay the same, 1, 5, 7, 1, 0, 0, 0, -13, 17, -3, 1, 0, and then I have 0, 15, 8, and 1, 0, 1. Again, I only ever change things below this diagonal. And so you can see as we keep applying these row 3 operations, the matrix on the right side here is going to remain lower triangular in the sense that the only entries that are non-zero other than the diagonal are going to be the things below the diagonal. So now we have to do one more operation. And the final operation we're going to do is we're going to say row 2, or actually row 3, is going to be equal to row 3 plus 15 over 13 times row 2. The reason I'm doing this operation is what I want to cancel out is I want to cancel out this 15 down here. And after doing that, I'll have something that is actually in, well, this will be in upper triangular form, and this will be in lower triangular form. So, let's do it. The first 2 rows do not change, so I have 1, 5, 7, 1, 0, 0, 0, negative 13, 17, negative 3, 1, 0, and then here I'll have 0, 0, and then here will be 8 plus 15 times, actually let's just do this in Wolfram Alpha. Eight plus 15 times 17 divided by 13. So 359 over 13. And the other one is fortunately a little bit easier to do. So I'm going to add 15 times 15 over 13 times negative 3 to 1. So 15 over 13 times negative 3 plus 1. This will give me negative 32 over 13. And then here, I'm just going to get 15 over 13. And then finally, I'm adding 15 over 13 times 0 to 1, which is just 1. All right, and that completes the process. So let's study the results it just gave us and try to interpret them. So after applying a sequence of row operations of type 3, we produced this matrix, and we'll call this matrix U. It's upper triangular in the sense that everything above this diagonal, or actually everything below this diagonal, is 0. And the things above the diagonal can be non-zero. On the other hand, this matrix over here is lower triangular in the sense that everything above the diagonal is 0, but things below the diagonal are allowed to not be 0. And so this is called L. And what we actually learn from this, if we study it, is that L times U is equal to A. And this is called an LU decomposition. Let's kind of verify that it actually works. So how about we compute some of this matrix multiplication? I don't want to do it all because it's kind of a messy computation, but I'm going to multiply 1, 0, 0, negative 3, 1, 0, negative 32 over 13, 15 over 13, 1, and I'm going to multiply that with 1, 5, 7, 0, negative 13, 17, and then 0, 0, 3, 5, 9 over 13. Okay. So let's see what we write down. Hold on one sec, I just have to study this. Why is that not quite working? Did I make a mistake in the computations? Did anyone see a mistake in my arithmetic when I was doing the row reduction? So let me just go through this real quick to see if I have an arithmetic error that slipped in. Because I think I did commit some sort of arithmetic error along the way. Oh, okay, so there is, this was supposed to stay -17. I lost the negative. So that might be why this is not working the way it should. Does this change anything else significantly? Alright, so there's some other arithmetic error in here that is preventing things from working exactly as it should. So let me do a simpler example. Rather than spend my time trying to chase down the error. Let's do this one. So let's set A here to be 2, 1, 4, 4, 5, -1, 2, 2, 9. And we're going to go through the same process again. And I know this one will work out because I actually did it this morning. So what we do is we take A, we form the augmented matrix. 2, 4, 2, 1, 0, 0, and 0, 1, 0, 1, 5, 2, 4, -1, 9, 0, 0, 1. So, what we're going to do is the first thing we'll do is we'll set row 2 to be equal to row 2 minus 1/2 row 1. If we do this, we'll have 2, 4, 2, 1, 0, 0, 0, and then 3, and then 1, and then -1/2 here, and then 1, 0. And I'm also going to set row 3 to be equal to row 3 minus 2 times row 1. So I'll have a -2 here, a 0, 1 here, and this 4 will become 0. And I'll be subtracting 2 times 4 from 1, so I'll have a -9. And I'll be subtracting 2 times 2 from 9, so I'll get a 5. Now, the last thing I'll do is I will take this matrix, and I want to put it in strict triangular form, so I'm going to set row 3 equal to row 3 plus 3 times row 2. And by doing this, I use this 3 to get rid of this 9. And I get 2, 4, 2, 0, 3, 1. The other side of the bar doesn't change, so I'll have negative 1/2, 1, 0. And on the bottom row, I'll have 0, 0, and then 3 times 1, actually 3 times 1 plus 5 is 8. And then 3 times negative 1/2 plus negative 2. So it's this, which is precisely going to be, why is my mind failing me? It's negative 7 over 2. And then 3 here and 1 here. Wait. I see. Okay. Sorry, I figured out what was going wrong. So we have to do things slightly differently. The basic process we're doing is kind of correct, but it's missing one fundamental ingredient. So let me explain what it is. As we're doing these row operations, let's think about how we're doing them. So we subtract 1/2 row 1 from row 2, and then we subtract 2 times row 1 from row 3, And then finally, we set row 3 is equal to row 3 plus 3 times row 2. So you get 3 different operations. And what we're going to do from these operations is we're going to form another matrix that's related to this one, but is somewhat different. So the way you form the matrix is as follows. You put 1s down the diagonal, and we're going to mark off kind of the operations we went through. So first off, when I was going from the row 2 I had here to the row 2 I had here, I subtracted 1/2. But rather than subtract 1/2, I am going to put over here positive 1/2. And this positive 1/2 is going to correspond to this change. Now, for this change right here, this is where I took row 1, and what I did is I subtracted 2 times row 1 from row 3. I'm going to put a positive 2 here. And this positive 2 corresponds to the fact that I am subtracting row 1, or 2 times row 1 from row 3. And then finally, down here, I'm adding 3 times row 2 to row 3. And so over here, I'm going to put a -3. And this is the matrix that I actually want. This will be my L. So I want to explain why I just ran into an error when I was doing this. There is a relationship between this matrix and this matrix. And I was having a brain fart. The correct relationship is that this matrix L is the inverse of this matrix. So one way to get L would be to first compute this and then compute its inverse, and you find that its inverse is this. But another way to compute it is actually just to kind of remember the sequence of row operations you use and remember how you undo them. So if you were subtracting 1/2 of row 1 from row 2, you put positive 1/2 here. If you are subtracting 2 times row 1 here, you put positive 2 here. If you're adding 2, you put -3. Or if you're adding 3 here, you put -3 here. And so that's how you form L. And so the relationship between L and this is that this is L inverse. So now let's actually see how the decomposition works. We have our matrix that we computed. In this case, I'll just copy and paste everything that's relevant. I don't want this anymore, but I do want this. I'm going to call this U. And I'm going to also take the L that we computed over here and put that down. And what I'm going to verify is that L times U is equal to A. So this will be a computation. So I'll take this, put it right here, and I'll take this, put it right here, and I'll compute the product. So if I multiply this first column by this first row, I get 2. If I multiply this column by this row, I get 1. If I multiply this column by this row, I get 4. If I multiply this column by this row, I'll get a 4 here. this column by this row. Well, 4 times 1/2 plus 3 times 1, I get 7. And, wait, no, I'm being an idiot. I get 5. And then I multiply this column by this row. 4 times 2 minus 3 times 3 is 8 minus 9, so -1. And then I take this column, multiply it by this row, I get 2. This column, multiply it by this row, I will get 2. And this column by this row, I will get 2 times 2 minus 3 times 1 plus 1 times 8, I get 9. And this is exactly the matrix we started with. Okay, so that is how you form the LU decomposition, where L times U is equal to A. Let me do one more example. So how about we do 1, 3, 2 here, and then 1, 4, -10 here, 1, 7, -1 here. So this is my matrix A, and what I want to do is I want to form an LU decomposition for it. So I am going to go through the operations, the type 3 operations needed to accomplish that. So the first type 3 operation I can do is I can set row 2 is equal to row 2 minus row 1. This will give me 1, 3, 2. And here I'll have 0, 1, -12. And I can also set row 3 equal to row 3 minus row 1. And so on the bottom, I'll get 0, 4, -3. And then finally, I can set row 3 equal to row 3 minus 4 times row 2. If I do that, I get 1, 3, 2, 0, 1, -12, and then 0, 0, let's see, 4 times -12, or -4 times 12 is 48, 48 plus 3 is 45. Okay. So this matrix right here is now in upper triangular form, and we call it U. And now we can figure out what our matrix L is. So there's two processes of doing it. One is that you could have done what we did before and kind of looked at this augmented matrix and at the end computed the inverse of this. But you can also just take a shortcut, and we're going to take the shortcut. And the shortcut is to use what we know about all these different row operations. This one, and this one. So I put a 1, 1, 1 here, 0, 0, 0 here. And because I subtracted row 1 from row 2, I'm going to put a positive 1 here. And because I subtracted row 1 from row 3, I'm going to put a positive 1 here. And because I subtracted 4 times row 2 from row 3, I'm going to put a positive 4 here. And this gives me an L, and I have a U. And what I want to verify is that when I multiply L with U, I get A. So let's do it. I have my L, and I have my U, and we're going to form the product. And if I multiply this column with this row, I get 1, this column with this row, I get 1, this column with this row, I get 1. This column with this row, I get 3. This column with this row, I get 4. This column with this row, I get 7. This column with this row, I get 2. This column with this row, I get positive 2 minus 12, so negative 10. And this column with this row, I get 2 minus 48 plus 45. So that is going to be just negative 1. And you'll note that I have recovered my matrix A. So this is called an LU decomposition of A. So we won't have much use for them throughout the rest of the course, but I do want to say one important thing. Whenever kind of computers are trying to actually solve linear systems, they don't usually just do like the full Gauss-Jordan elimination process. Instead, they attempt to compute the LU decomposition and then basically study the parts L and U separately. And there's a variety of reasons, which I don't really want to get into, on why this decomposition is very useful for computational applications. You do not need to know how to compute it, but it's not going to come up much in the future. So that is all I have to say on matrix inverses and row operations. So there's one final bit of business that we have to take care of on chapter 1, which I've been saving to the end because it's kind of weird, but it is important. And the final bit of business is transposes. So I have always thought matrix transposes were kind of weird, not because they're hard to compute. In fact, they're extremely easy to compute, but because they're somewhat less intuitive than a lot of the other things that we've talked about. And there is an intuition for them, but we won't be able to talk about it in this course. But you're going to see them come up over and over again in various applications, in particular much later when we talk about QR decompositions. So here's what a matrix transpose is. Suppose you have a matrix A. And let's say it's a n by m matrix. And A will have n rows and m columns. So here I'll have A11, A21, blah, 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 all the way down to AN1, all the way over to ANM. Here I'll have A12, all the way over to A1M, and so on. What we're going to do is we're going to take this matrix and we're going to transform it into another matrix. And here's how we do it. Then A transpose, and we denote the transpose with a T, is a M by N matrix. So I want you to pay very, very close attention. We're shifting the role of N and M. So if before we had N rows and M columns, now we're going to have M rows and N columns. Defined as follows. So here I'm still going to have A11, but now I'm going to swap the A12 with the A21. So here I'll have A12, here I'll have A21, and I keep going all the way over until I get to AN1, and I keep going down until I get to A1M, and so on. At the very end, you still have A and M here. But now you have N columns and M rows. If you want to write this formulaically, the ij component of AT, and this is the thing in the ith row and jth column, is the thing in the ji component of A. So the way I usually like to picture this is I like to imagine that I'm taking my matrix and I'm just sort of spinning it around. I'm flipping it in some sense. And like, this is kind of easy to illustrate if I had a book in my hand, but I don't. So I'm just going to give you some really simple examples. Let's suppose I have the matrix A that looks like this: 1, 5, 6, 7, 8, 9. Now then I can figure out what the matrix A transpose is. First off, I note that I have 3 rows here, 2 columns, so I'm going to have 2 rows and 3 columns. And I just kind of flip it around. So here I'll have 1, and then I'll have 6, 8. And then down here I'll have 5, 7, 9. So if you want to like imagine what you're sort of doing is you're taking this corner of the matrix and this corner of the matrix, and you're flipping them over while you're leaving this corner and this corner the same. Like, imagine that there was kind of like a bar here, and you were just rotating the matrix around the bar. And so if you had 1, 6, 8 here, you get 1, 6, 8 here. 5, 7, 9 here, you get 5, 7, 9 here. So we'll do one more example. Say A is 3, 2, 7, 8, 4, 6, 0, 1, 10, 0, 0, 1. Then I can compute A transpose. And A transpose here, well, this is 4 columns and 3 rows. the transpose will have 4 rows and 3 columns. And I imagine that I'm holding this fixed, and I'm interchanging this edge with this edge. So if I have 3, 4, 10 here, now I'm going to have 3, 4, 10 here. If I have 2, 6, 0 here, then I'm going to have 2, 6, 0 here. 7, 0, 0 here, I'm going to have 7, 0, 0 here. 8, 1, 1 here, I'm going to have 8, 1, 1 here. So that's how transposes work. They're very, very easy to compute. And what we're going to do is look at some applications of them. So, the first thing I want to say actually is suppose we have our matrix A and we take the transpose of it. Then we get our matrix A back. So this is easy to see because what you do is you imagine flipping about this diagonal twice. So you start here, you flip to this, but then if you flip back, it flips back to this. So if you take the transpose of a transpose, you get the thing you started with back. Also, if you multiply a matrix by a scalar, and then you take the transpose, this is in fact the same thing as multiplying the scalar by the transpose to begin with. Likewise, if you add 2 matrices and take the transpose, and then you, this is just the same thing as taking the transpose of each of them individually and then adding them together. Now, the final identity here is the most subtle one, which is that if you take the transpose of the product of 2 matrices, this is the same thing as taking the transpose of B and taking the transpose of A and multiplying them together. But note that there's an order reversal that happens. And this is really subtle. So I'm going to try to explain why this is true. Suppose C is equal to A times B. Then we have that by the formula for matrix multiplication, Cij is going to be equal to the sum from, maybe I should specify, A is n by m, B is going to be m by k, so I'm going to be summing from s equals 1 to m of A is times B s j. And this is how we compute the components of the product. Now, let's look at the transpose. So if we denote D by C transpose, then the Dij is precisely going to be equal to Cji. Now let's also compute B transpose with A transpose. Well, if I denote the components of B transpose by lowercase b with a t, ij, and I do the same for A, then I can study the product of them, and I can look at its components. So d prime ij here is going to be equal to the sum from s equals 1 to m of b ij, actually, sorry, b I s times a s j, but note that the component of the transpose is actually just the same thing as bji, and likewise the component of A transpose here is the same as AJI, so this is in fact the same thing as the sum from S equals 1 to M of AIS times BSJ. So that is going to be the same thing as this. And oh wait, no, there's one mistake I made. This right here should actually be, it should have stayed a J, and this should have stayed an I. So I compute d prime ij to be this, and this is going to be exactly the same thing as cji, but as we've verified over here, the transpose of c, the ijth component of it, is cji. So this shows that d is equal to d prime, and both sides of this equation are equal. So it's by far the most complicated rule for transposes. And here's the main consequence. Suppose A is an n by n matrix, then A is invertible if and only if A transpose is invertible. And here's why this is true. We're going to use the thing we proved earlier, the first theorem of today. No, that's not it. Where is it? Here it is. We're going to use this theorem. And the reason this theorem is going to help us is because it says that A is non-singular if and only if A is row equivalent to I. So suppose A is invertible, then A is row equivalent to I, which means there's a sequence of elementary matrices EK times EK minus 1, blah, 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 all the way until E1 times A, such that this is equal to I. Well, we'll call this B, and so this becomes I is equal to B times A. And we're going to take the transpose of it, and so we'll have I transpose is equal to A transpose times B transpose, recalling that transpose is order reversing. But the fact we really use here is that I transpose is just equal to I. The reason this is true is recall what the identity matrix looks like. It's 1, 1, blah, 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 1 along the diagonal from the northwest to the southeast, and then zeros everywhere else. And so if you flip this matrix, where you imagine you take this edge to this edge, then what happens when you flip it? Well, you just get the same thing. You get ones on the diagonal and zeros everywhere else. So I transpose is equal to I, which means A transpose times B transpose is also equal to I. So this tells us that there exists a matrix that when you multiply it by A transpose, you get the identity matrix, which means that if A is invertible, A transpose has to be invertible. On the other hand, you could simply repeat the same argument in reverse to show that if A transpose is invertible, then A has to be invertible by using the property that the transpose of the transpose is just the original matrix. So that is all I have to say about transposes for the moment, but they will come back soon. And now I'm going to introduce something else. And this is going to start chapter 2, determinants. So before I finish today, I want to leave you guys with a simple calculation. Suppose we're looking at a matrix A, and let's denote its entries by variables. So we have A11 here, A21 here, A12 here, A22 here. Let's try to do the Gaussian row reduction process. But let's do it abstractly, just using these variables. So let's maybe make a simple assumption to begin with, which is that A11 is not equal to 0. Because if A11 is not equal to 0, then what I can do is I can take the first row here and I can subtract it from the second row. And if I do that, well, I'll set row 2 to be equal to A21. Actually, I'll write it like this. I want to cancel out this A21, so I'm going to subtract A21 divided by A11 times row 1. And so I'll have an A11 here, an A12 here. Here I'll get a 0. And then here I'll get an expression. And this expression will be, let's see. So if I subtract A21 over A11 times row 1, that means I'm going to have A22 minus A12 times A21 all divided through by A11. And I want to study this expression for a minute. Because if I study this expression, what you see is that you can combine it into a single fraction, and your single fraction will look like this. everything will be over A11, which you're presuming to be not 0. And you'll have A11 times A22 minus A12 times A21. And maybe this expression in the numerator is familiar to you, because you probably learned about it if you took multivariable calculus. But if you haven't, this right here is the 2 by 2 determinant. It's what you get when you multiply this entry by this entry and subtract the product of these two entries. And it's naturally showing up when we do the row reduction process. And in fact, there's a very, very simple observation we can glean from this calculation. Assuming A11 is not equal to 0, then A is invertible if and only if A11 times A22 minus A12 times A21 is not equal to 0. So this is a really simple result that follows from a really simple computation. But what's amazing about it is that we can actually generalize it to n by n matrices. And we can find a polynomial expression in terms of these coefficients such that a matrix A will have an inverse if and only if the polynomial expression is not 0. And I will show this to you guys on Monday. And I hope you guys have a good nice weekend. I'll be available for office hours starting now. So if you want to talk about the homework, there was one due today by midnight, and there's also one due Monday at midnight. You can hop in the general channel in the server and ask me whatever. So I hope you guys have a nice rest of your day. Marcus Link asks, will we need to memorize the proof of 4? No, I will not ask you to memorize any proofs. I do expect that you'll be able to prove certain basic things, but they won't be things I ask you to memorize. Mostly, I want you to understand the computational processes involved and how to execute them. Like understanding how matrix inverses work, how to compute them, the properties of matrix algebra that we talked about this week, stuff like that. You don't exactly need to know the proofs. Okay, so if that's all, I'm going to go off live stream, and if you want to talk to me or ask questions, join the general chat in the Discord.